Thank you. Thanks for standing up. So thank you, Masood and Tirshad, for organizing today's session. My talk is going to be on implantable devices. So I'm going to discuss wireless power and wireless links for implantable devices. It's going to be a little bit more on the application side of this session. I saw that many of the talks are on particular technologies and specific blocks. This sort of cuts across different blocks and goes into the applications. And one of the things I'm going to do is I'm going to give examples. So the talk is going to cover a lot of examples of different implementation of these implantable devices, each of which hopefully provides sort of an overview into the specifics of how things are done. So before I get into the main talk, let me give you an overview of what the activities of my group. So we work on 3 different areas. We work on IoT devices, whether it's millimeter wave systems or wireless power delivery, backhaul systems. We also work on sensing and imaging for a variety of applications. Today's talk is going to be a part of the biomedical devices group in my group, which is on implantable devices. So we work on implantable systems, on how do you really miniaturize implantable systems and put them into various different applications. And before I start, I wanted to sort of acknowledge the work of the group, which is I'm going to present today. So let me zoom out a little bit and talk about the application of biomedical from a circuit and system perspective. What are the opportunities we see in biomedical devices? If you zoom out and look at mortality rates and the causes of mortality in the US, and I'm guessing worldwide, number 1 is heart disease, number 2 is cancer. What's interesting is if you plot the mortality rate from 1980s to about today for heart disease and cancer, you see that for heart disease we have a factor of 2 reduction based on changes in diet, different procedures, better monitoring systems, and so forth. But for cancer, the problem is almost flat. So we don't really see a reduction in mortality rate on the net, on the average, from cancer from 1980s to 2010 and 15. So when I started out my research, this was sort of an eye-opening graph, because what it showed is really after all of these technologies that we've introduced in our healthcare system, whether it's monitoring, better imaging devices, PET, CT, MR, the average rate of cancer mortality rate as a net hasn't changed. So that was a problem. Now, if you look a little bit deeper and see why is for a particular disease, whether it's cancer or any other disease, this is a problem, you see that it really boils down to our sampling of the healthy and disease states. So these are different disease states. This is for cancer progression, but you can plot this for any sort of disease. And different disease progress at different rates. And the problem is you have a fast-growing cancer which goes from not being detectable to 4 metastases in a very quick set of steps. And because the way we screen our body today, whether it's cancer screening or going to the doctor is every 18 to 24 months, we really catch these fast-growing disease cycles. So we've introduced a lot of systems, interventional, diagnostic, but from a screening perspective, we're still limited by the fact that the frequency of screening intervals. The frequency is usually set by either cost, effectiveness, or safety. And for cancer, this is definitely a big problem for early detection. But if you contrast that to any system we design, if you look at any engineered system today which has a lot of electronics, it could be a jet engine, it could be an electronic chip, we see that we take a very different approach. Every electronic system you and I design in this community, we have a lot of calibration loops. We have one before cold calibration. We have on-the-fly runtime calibration. So, for example, a jet engine, this is a slide I pulled from our Precision Health Institute at FIND. They contrast this to how we work with our bodies today, how we monitor the human body today. A jet engine generates about 10 terabytes of data per 30 minutes of flight. And contrast that to going to the doctor every 12 months and taking your weight, your height, and blood pressure. So we see a very different contrast between how we sort of monitor engineered systems and the human body. So in my world, what you want to do is you want to look at an equivalent of continuous monitoring, or what we call NICUS monitoring in this sense. And that would be longitudinal studies. And longitudinal studies are essentially looking at several fixed parameters over time and really deciding by the changes of these parameters, not necessarily by the absolute sense. So for example, I'm just getting a little bit of echo, I'm just turning it around. Too bad. Yeah, that's okay. I mean, I think I'm okay with it. So, so if you look at, for example, longitudinal studies, we want to look at the delta differences between the samples as opposed to taking an absolute. So when you would go to the doctor, you might have a screening system that does mammography. And what the doctor needs to do is take a mammography scan and right there decide this is cancer or not. And there's a lot of false alarms related to a screening like that because there are differences in the physiology of the bodies, there are differences in different cycles. But if you look at differences over time, the hypothesis is that there's a lot more data. So this is the equivalent of doing Nyquist rate healthcare for screening technology. So in very broad terms, if you plot screening technologies or healthcare technology in two different axes, one is utility, the other one is frequency of testing. We have really two regimes that are going on in terms of activities, at least what we see out there in the valley. One is that what I would call NIH territory, which is very fundamental and it's been very crucial in the past 20, 30 years in improving healthcare and outcomes. And these are advanced technologies. This is the PT, the PET, CT, MR combined systems. They are very low in terms of frequency of testing, but very high utility or the quality of the metrics you're measuring. On the other end of the spectrum, you see a lot of startups looking at continuous monitoring of simple parameters. Pedometers, activity monitoring, your health, your Apple Watch might be measuring your heart rate. So these are parameters that have lower quality for diagnostic purposes, but you're measuring them over longitudinal distance. And what we're proposing is that for a technology to really be transformative for these applications, you really need to have high utility and high frequency of testing. So this is why we sort of envision as Nyquist Health in this regard. So in order to enable Nyquist Health, these are sort of the three intakes or research directions that we're thinking about. One is closer integration of electronics and the human body, and as you can imagine, this is where our community could play a central role. The second is thinking about sensing and monitoring, but also therapy and closed-loop systems. So this is not just about measuring, but it's also about activating different pathways with closed-loop systems. I'll talk a little bit about this today. And in terms of platforms, we have implantables, ingestibles, and wearables in mind. So implantables we're going to talk about today. Ingestibles are devices that one-time use, you swallow, it goes through your GI tract, measures the GI tract, various different parameters, and then they're just data is wirelessly transmitted to your receiver. And wearable devices, you can imagine, are devices that can provide better sort of maybe imaging capability or better look window inside the body. So the technical challenges of many of these systems really boil down to three things. One is miniaturization, which obviously means the size miniaturization, but means that the power consumption has to be really lowered to a point that we can put these devices millimeter scale in the body. One is physical sensing technology. So if we're able to put small millimeter-sized devices inside the body or ingestible system, we have to start thinking about new ways of sensing or imaging in the body. We can't really think about the traditional ways, we restrict ourselves to the traditional ways. We have to start thinking about new modalities that might be a better fit for this sort of a platform. And third is innovation on end-to-end system design. A lot we're going to talk about, the real innovation is about designing the whole system from the beginning, physical phenomena, all the way to packaging and putting it in a small form factor so they could be injected in the body. So that sort of thinking usually is not central, at least I should say. I've been in this community for a very long time and I've been designing a lot of chips, but the way I designed a lot of chips in my early stage of my career was you design a chip, you measure it, and it's done. And you move on to the next project. In fact, I have a drawer full of chips there that have been measured and submitted, and once the chip is designed and we've shown it works, it's done. In this sort of system, you really have to do proof of concept all the way there. Oftentimes, we put it all the way into the in vivo studies. So that would require a little bit different way of thinking about how you design the system. So today's talk, as I said, is just going to be on implantable devices. I'll start giving you an overview of why we're focusing on ultrasonic links as opposed to RF links for this particular application. I'll give you an overview of that. And then what I'll do is I'll give you 6 examples of projects. So 5 of these projects are projects that we've published in elsewhere in conferences that really show how this platform could be used for implantable systems, is ultrasonic wireless power and data. And at the end, I'm going to talk about ultrasonic MIMO. And the reason I need to get into ultrasonic MIMO is that the elephant in the room when you use ultrasound is the data rate. We use a carrier of about 1 to 2 to 5 hertz, depending on the application. And what you see is that when you're using a carrier of 1 to 2 to 5 megahertz, and if you want to have a 10 megabit per second, 100 megabit per second link, there's a bit of a problem there. And as opposed to RF systems which operate at a gigahertz. So we need to start thinking about ways to increase the data rates if we're getting into ultrasonic communications. And this is where the ultrasonic MIMO comes in. So let me start by giving you the overview of what the goal of this project is. So what we're looking at is implantable systems that open up new applications. So these are not implantable systems that are for current applications out there for pacemakers, deep brain stimulation, and so forth. We're looking at opening up the applications to many more scenarios. And in order to the first step in getting into these applications is invasiveness. If you want to put an implant in the body, and that requires a very massive surgery, a brain surgery, or a big piece of device, electronic, pulled into the body, you're restricting yourself to use cases which what we call the last resort. So the patient has no other option. They have to put in this big device in the body. Nothing else must have worked. So this is the scenario that's very limited. So invasiveness, which means that we need to miniaturize, and means that if you miniaturize, not only it becomes less invasive in the insertion point, but the body response, which is a big effect, would also be reduced. So that's the first thing we need to think about. The second is once you have now a capability that's miniaturized, you'll be able to open up the application spaces to new treatments and new measurements. And we're going to talk a little bit about what we mean by new treatments and new measurements. And an example of that is what we is closed loop systems. So this is a graph I borrowed from our program manager at DARPA. This is a closed loop system overtaking a specific organ failure in the body. So if you think about the human body, it's basically many of the organs are controlled by the central highway, which is the nervous system. And the electrics program, the idea of the electrics programs was that if you want to overtake the function of a specific organ, what you need to do is you measure the output of that organ and you control the nerves that go into the organ. So by that system, if you put it in a closed loop system, you can overtake or at least complement the function of that particular organ. An example that we're working on is bladder. This is an easy one. So if you think about the bladder, people who have continence issues or bladder emptying problems, what the output parameter is pressure. So you measure the pressure in the bladder wall. As the pressure grows, that means the bladder has to be emptied. And then you control the nerves that go into the sphincter or nerves that are controlling the bladder itself. So by putting these two in a closed loop system, you can control or overtake the control of the bladder. There are many more examples that are more complicated, but bladder is one circuit to kind of understand from a medical side, and so that's what we're focusing on, the bladder system. The cardiovascular side has been around, actually more advanced version of taking control of a pacemaker. That is exactly what a pacemaker is. You measure, you know what the output is supposed to be, and you use a pacemaker to control the electrical activity in the heart. But as I said, if you contrast that to today's medical systems, they're usually large, very invasive. The applications are very limited because of the size and the. So how do you make implantable systems? First thing you have to think about is how do you get power into these implants before even thinking about communication. And the way you think about power is most traditionally by a power delivery in a near field by coil-to-coil power transfer. This system is safe, it's robust, it's FDA approved. There's a lot of systems out there that's being used by sort of a near field or coupling systems that are being utilized. And even copied here at one of the early figures of this system from Tesla's patent in 1914. I think this is the right patent number, but I could be mistaken. I was just searching for that recently. So the efficiency of these systems really depends on the coupling coefficients and the quality factors. So if you get a sufficient coupling coefficient and you have sufficient quality factor, you can get a very high efficiency. And this is how your Apple Watch is being charged, very close distance, very controlled alignment, and then the charging efficiency could be very high. So the question is, why do we need to think about anything more than coil coupling? And there's a lot of reasons that I've listed here, but the most important of which is that the coupling coefficient really drops down with distance to size. So if your coupling coefficient starts out being 20, 30%, it exponentially drop as you go further away, so the distance goes larger, or the sizes are miniaturized. So distance to size really controls coupling coefficient. So that presents a fundamental challenge when you think about sort of the use cases. Many of the applications today, you're very close and the coils are decent sized. So coupling with coil-to-coil transfer is very efficient. But as you try to go deeper, 10 centimeters deep in the body, and have an implant that's millimeter sized, coupling through this mechanism is no longer going to work. So the next mechanism you can think about is far field RF transfer. And the problem with far field RF transfer is even in the body, the wavelength of RF we're going to use at the gigahertz of frequency, gigahertz, couple of gigahertz of frequency, the wavelength is very large. So when the wavelength is large and your implant is small, there's a couple of problems that are fundamental, the physics side of the problem, not even the circuit side. Number one is that the large wavelength means that from a diffraction theory perspective, you can't focus the beam. So what you see on the top right here is the effect of wireless power transfer with RF technology, with far field RF or propagative RF technology. And you can see that there's quite a bit of heating, not just at the implant side, but the surrounding. So most of your energy is dissipated in tissue. And tissue is dissipative. At RF frequencies, that's how your microwave oven works. It works about 2.4 gigahertz because water absorbs a lot of energy at that frequency. So that's problem number one. Problem number two is even if you get the energy in, the efficiency of your antenna, when it's considerably sub-wavelength, and it's much smaller than the wavelength, is going to be very small. And this is, again, is limited by the physics of the problem. It's not necessarily limited by how we design our circuits. So these two systems, again, limit how deep you can go and how small you can make the implants. Again, if you're going to 2-3 centimeters and your implant is a few millimeters, this might be a better technology compared to a coil transfer. But if you're going to get 10 centimeters deep, and remember the problem of bladder control, if you think about putting an implant to measure the pressure in the bladder wall, this could be 10 to 15 centimeters deep in the body, depending on the individual. So these kind of problems gets much harder to think about RF power transfer. Now let's think about ultrasonic power waves. So ultrasonic waves have been used for a variety of different applications. The most commonly is for imaging. So ultrasonic waves are mechanical waves that are disturbances in the medium. On the left, you see just omnidirectional waves from a certain source that's propagating outwards. On the right, you see a focused version of that. So this is an F2 transducer with a diameter of 3 centimeters of focusing at 6. We're using a 1 megahertz 10 cycle wave at the loss of 0.8 dB per centimeter. So this is a loss about what you get in the human body. And you can see that we can pretty efficiently focus the energy deep into the body without having most of the dissipation at the surface. Now, ultrasonic waves have been used for a variety of different power transfer for a long time. People have even some papers very early on, many years ago, have even looked at ultrasonic power delivery through a concrete wall of a nuclear power plant. When you don't want to have any system or wires that go from inside to the outside of the plant and you want to completely isolate things, you can power a lot of energy through the wall, through the concrete wall, using ultrasonics. But the challenge here for implantable is going to be miniaturization. How do you make these systems into millimeter and sub-millimeter? And the second challenge is going to be communication and power simultaneously. So this is what we started thinking about from a circuit and system side into this application. The reason we started thinking about ultrasound is the speed of sound. And so speed of sound is 4 to 5 orders of magnitude slower in body or air compared to RF. So in air, it's about 5 orders, in body, it's about 4 orders of magnitude slower. What that fundamentally does is that the wavelength of ultrasound is going to be considerably smaller for a given frequency. Or alternatively, we can use a megahertz ultrasound and get about a 1.5 millimeter wavelength in the body. And that means that I can match the wavelength of my propagating waves to the size of the implant. And that's going to be the fundamental difference between RF and ultrasound. Number one, it allows us to focus. So I can go 7 centimeters deep and still focus to a millimeter size dimension. This is not possible if we're doing RF technology with 5 or 6 centimeters away. So that's number one. Number two, I can operate a network of implants. So I not only go from one transmitter to one receiver, if I have multiple receivers, I can simultaneously operate with these. And we've been using a lot of that technology in beamforming in a lot of millimeter wave RF systems. We can apply the same methodology to ultrasonic systems. So that's the second advantage. And the third is the high efficiency. So once the receiver is now resonant, the efficiency is going to be significantly higher than a non-resonant system. So these three together make implants operating with ultrasound an appealing sort of a scenario. Some additional benefits here. One of them is that tissue attenuation is considerably lower in ultrasound. Ultrasound is safer, causes less heating. It's been used for a variety of applications with ultrasound imaging, with the sonogram. So it's very safe, so to speak. The FDA limit intensity is considerably higher in ultrasound compared to RF because of the same reasons. And ultrasound beamforming allows you to get around a lot of the obstacles. And this is an easier than done sort of problem. I only point here, but there's a whole research program on how do you get around obstacles. But in theory, because I can do beamforming, I have a lot more degrees of freedom in operating ultrasound as I do compared to RF. So that provides an appealing technology for this sort of application. Since 2012, and when we started the technology, it was all about characterization and modeling. This is one of the first steps of any time you design a circuit or you bring a new technology, a MEMS or an antenna into your circuit, is you want to really understand the model of this device and be able to design circuits around it. So modeling efforts, modeling, the mechanical and electrical modeling. And we designed the first really kind of miniaturized system around 2013, 2014, which was a hybrid operating system. I'm going to talk about that a little bit today. So that was proof of concept. The first couple of years was just proof of concept that we can operate with ultrasound. The theory works. We can model it. We can make it efficient. The second generation devices were all about functional. So we took a lot of the functions that were out there in implantable systems today with RF, and we try to translate that into ultrasonic systems. So the first one is implants for duplex communication, so we can do communications uplink and downlink. We can release drugs. This was a collaboration with the biochemistry department. And we can do optical stimulation for optogenetics. So that was the second generation. The third generation got into more complex sort of a function. So we're thinking now about pressure sensing. This requires a high precision electronic system built into the implant. This is about 10-bit resolution pressure sensor. I'm going to talk about that today. Multimodality stimulation, so we go controlled stimulation as opposed to this one here, which was direct stimulation. Controlled stimulation means that I can program the pulse width, the pulse height, all the parameters of the pulse. And third, I can do beamforming from the outside device going inside. I can control the different parameters of these implantable devices. Now that was the third generation, and more recently we're getting into functions that were previously not possible for implantable systems. And what I mean by that, we have two applications right now that we're working on. One is imaging. So when we think about implants, we don't necessarily think about imaging systems. We think about basic functions, stimulation, sensing, one-bit scalar. Imaging, you need an array, you need an ultrasonic receiver array, you need some kind of stimulation. So this is much higher in terms of complexity that we're adding to the implantable system. So this is what we did last year in VLSI, presented VLSI last year. And now we're also looking at aptamer detection. So that is basically doing protein level detection for a variety of applications. So these two last applications were not possible because of the power constraints in previous generation of implants. Now are becoming possible when you have 1, 2, 5, or 10 milliwatts available at your implantable system. So I'm going to start zooming out and talking about the implantable system from a sort of a top-down. If you look at the entire link, think about link budget and wireless communication. We have a transmitter array. It's focusing the energy to a small miniaturized implant. The implant itself has a transducer, some kind of a rectification of energy for power conversion and communication, and then there's a load. So that's the whole system looks like. So you can imagine the efficiency is going to be in two parts. The efficiency from a power link efficiency point of view is going to be the transmitter efficiency. How good can I focus from this transmitter to this receiver? And then I have an available power at the receiver. And the second part is how much of the available power were you able to recover and put into your electrical load. So these are the two efficiency components. Let me start with the implant side of things, and I'll go to the transmitter next. So on the implant side of things, we have the efficiency of the receiver has 4 components. It has the aperture efficiency. I'm going to talk about what aperture efficiency is. Essentially, aperture efficiency is how much of the received available power intensity were you able to pick up from an acoustic to electrical point of view. There's no rectification yet. It's just picking up from acoustic to electrical. And you're normalizing to the available power intensity that's available at that aperture. Right? So that's the aperture efficiency. It's exactly the same definition, by the way, if you've ever designed antennas, it's the same thing. Then we have matching efficiency. We have what the receiver system looks like. The one that I'm going to focus a little bit more because it's different compared to the systems we've designed is the first one, the aperture efficiency. The rest of these we see in any other power recovery system out there, any other RFID system out there. So let's look at aperture efficiency. As I said, it's the ratio of effective aperture to the physical aperture.
And one thing to keep in mind, this was a sort of a fusion early on when we were putting out our first set of papers. Aperture efficiency could be larger than 1. And this is true for antennas. This is also true for ultrasonics. When you go to sub-wavelength aperture sizes, or when you have a dipole, the physical size of that dipole is 0. There's no physical area with the dipole. But a dipole antenna still recovers energy. So the aperture efficiency is not limited to 100%. It could be higher than 100%. People have shown it in optics, that you can have scattering of sub-wavelength sizes. People have shown it in antennas. It's pretty understood in these two fields. In this field, is the same thing. If you go down in size, smaller than the wavelength, the aperture efficiency could be larger than 100%. And see that this measurement. Don't get confused if you see anything more than 100%. In this particular case, that's fine. So use different materials. So here I'm showing PZT4, PZT5, and barium titanate. We also do lithium niobate, a different set of materials. We look at flexible materials, non-flexible. Some of them are better suited for in-body applications compared to others. And the figure of merit here that I'm showing is the aperture efficiency in red. This is the PCE, and as you can see here, it starts touching 100% and going slightly above as you go down in wavelength. And then impedance. Impedance, the dotted lines are simulations, and the solid traces are measurements. So what we characterize transducers, we think about aperture efficiency, and we think about their impedance profile across frequency. If we capture these two, we're able to model the transducer sufficiently well to build it into our system. Now, what are the design variables? When we design antennas, it's mostly about geometry. Here, geometry plays a role, so dimension and geometry play a role, but there's also material, which has very vastly different properties when you go from one material to the second. If you compare single crystal and piezo, for example, compared to barium titanate, the speed of sound, the coupling efficiency, the K31, the dielectric constant, all of those are going to be very different. So material, dimensions and geometry, packaging, acoustic loading, and mechanical and electrical interfaces. These are the design variables. And oftentimes when we're designing these systems, we have a tank for characterization. So this is a transmitter sending energy to the receiver. The receiver, we're able to characterize propagation properties, what we call pitch catch measurements, where you transmit energy on one side, you receive, and you characterize not only the bandwidth, but losses, propagation, dispersion, all the effects that are required. We have different piezo materials that are housed in our custom packaging done at Stanford. We do air-backed or non-air-backed transducers, and I'll talk a little bit about these. So, and you try to model it, this is like any mechanical resonator. It's going to go through a short-circuit resonance, assuming that you have high enough quality factor. Short-circuit resonance and an open-circuit resonance. And the beauty is, between the short-circuit resonance and the open-circuit resonance, the transducer is really inductive. So you can, with a capacitive network, you can come in with a miniaturized on-chip capacitive network, you can come in and get full power efficiency across the whole band. I'm going to talk a little bit about this. But the operation is usually between the short-circuit resonance and open-circuit. And then you have different modes. So in short-circuit, open-circuit resonance, you have your longitude, length expander modes, and depending on the disk mode, depending on the aspect ratios. But you also have higher order modes that kick in, sliding at, for this particular piezo, at about 1.6, 1.7 megahertz. So all of these need to be taken into account, and I'm showing again the simulations and the measurements in solid and dashed lines. And you can see there's reasonable well match between our first order models and measurements. And I'm not going to get into the modeling too much here, but the 1D model, the KLM model we use, is the majority of our system. We take the KLM parameters, we fine-tune them, just like we do in BSIM models and transducers. We fit them to match the characteristics of the device. In some particular cases, we can't really use KLM 1D models. We have to go through full 3D. Those are very few cases that we're miniaturizing beyond, let's say 500 microns, 300 microns. You really need to take a look at the 3D model in those cases. What about air backing? As you can imagine, air backing for impedance, for acoustic impedance, is a short circuit. So when you air back, you double your efficiency because there's no energy going from the other side. You essentially make a resonator. So air back transducers have double the efficiency, more or less, compared to non-air backed. And as you can imagine here, we're going from short circuit resonance to open circuit resonance, and we can maintain a high efficiency. And the reason for that is, again, between the short circuit and open circuit, we're purely inductive. So a capacitive network could come in and maintain the full perfect match across the whole range. So we also miniaturization. Depending on the application, you want to miniaturize your devices. So here's taking a slab of piezo, thickness of 0.5 millimeters. 300 microns. And again, once again, the whole game here is to make sure that your models and your measurements have a good match so you can predict what the outcomes are going to look like. We still maintain a decent match between measurement and simulations in terms of miniaturization. And the short circuit resonance, as you can, this is, again, one of those things that you can't see in a 1D model. In a 1D model, there shouldn't be any resonant change. But once you go to a full 3D model, it becomes obvious that the short circuit resonance is going to shift as you make the size of the implant smaller. Because, I mean, the first order, if you want to think about it, think about a microwave cavity. And a microwave cavity has different modes that are coupling into each other, right? As the modes get closer, they pull each other left and right. And make the transducer narrower and narrower, the coupling between these different modes actually reduces. Because it goes from a square, which has a lot of degenerate modes, into something that doesn't have as many degenerate modes. If you don't have degenerate modes, the coupling gets reduced. And so there's I can give a different set of slides on that, but then the frequency goes up. So the same thing for efficiency. We want to be able to get the impedance and efficiency modeled, and we've done that to about looking at much smaller than these dimensions, and we're trying to see what are the avenues to go there. Now let's look at aperture efficiency. We've taken the piezo, we've reduced the size. For each one of these sizes, we've optimized the right frequency. And so I'm plotting here the size optimal for each frequency. We've optimized the frequency for power recovery, and I'm showing the aperture efficiency. And you can see here, aperture efficiency is all above 100%. The reason for that is I'm operating things at smaller than the wavelength. So theoretically, what you see is that if your size to wavelength is about 2 over pi, up to about 2 over pi, your aperture efficiency is about flat with size. And as you go smaller than 2 over pi, the aperture efficiency goes up. Because now your device is small, the wavelength is larger, and the device is recovering energy from the surrounding. It has a complex impedance. If you look at antenna as a dipole, if you look at the dipole and you go sub-wavelength, you've seen from your antenna classes that if you're a resonant dipole, the real part is about 50, 70 ohms, the imaginary part is 0. But if you take the same figure and you go down in wavelength or down in frequency, you see that the real part goes down, the imaginary part's getting large. So the complex impedance here allows you, gives you a different way to model the device. Now, what limits, why do we go up in frequency, why do we go up in efficiency and then drop, is that the losses are not going to scale with the same factor. So dominate and sort of limit what maximum efficiency you're going to have. And losses here means a combination of all losses. It's dielectric losses, but also the loss of that getting the energy out, connecting the piezo. That's going to be a larger fraction of the entire size when you're going to smaller sizes. We can plot now available power. So before I was the size parameter, available power does go up with more area. The larger you have your area, the more available power you're going to have. So what we expect is that as you increase the area, the available power goes up because of the area. As you go down in width, the aperture efficiency goes up. So again, your available power goes up, but your area is going down. So aperture efficiency actually goes up faster than the area goes down. That's the interesting part. But then losses kick in, and really you don't see that benefit, the theoretical benefit here. So the losses, the combination of losses and the area going down will actually dominate, and the efficiency goes down. So this is what you see, that the available power, actually the net available power goes down with the size of the implant. Okay, so now let's talk a little bit about what is the transmitter focusing. So this is where a lot of the numerical aperture techniques we saw in optics and we've seen in acoustics come into the picture. You have a transducer, it has some kind of a focus capability. And remember, here we're talking about a continuous wave. We're talking about power transfer. So when you have any kind of a transducer, any optical system with a certain aperture and wavelength, your focus is going to look like a grain of rice. So you have what we call a depth of field, which is the length in the focus, and you have a lateral focusing capability. Usually the lateral focus is better than your depth of field. So what you end up with is this grain of slice kind of a picture here. So what happens is, if you look at this dimension of this grain of rice, it could be controlled by two fundamental parameters. One is aperture, and the other one is wavelength. So as you go down in wavelength or higher in aperture, the focusing gets better. So if you compare a F3 transducer with an F1 transducer, an F1 transducer, you're coming closer and the transducer is bigger, it has much better focusing. So this is the effect we're showing here. For the same distance, if you have a higher frequency or a larger aperture size, the focusing efficiency is improved. Now, this is going to be fundamental in terms of figuring out how much of a focus we can implement. So we took it and we looked at its focusing capability at a given lens, at a given location, the transducer location. And physical location is slightly different than geometrical location. I'm not going to get into that, but that's just coming out of the ultrasound wave constructive destructive interference. So we have a radius of a transducer. We also have a radius of focus. As you can see, as I bring my focus closer and closer in, the focus efficiency goes up because I'm getting a larger effective aperture, or I'm getting a smaller F number. So as you get closer to the transducer, the focusing gets better. And you can see that in optics it's the same thing. As you get closer to your aperture, you can do better focusing. So this is the second effect you see. Now this effect leads to, something interesting. And that is, if you want to focus at a given location, let's say I want to focus to 8 centimeters deep in tissue, right? And I have two options. On that desired location, so that's what we call a focal peak or focus peak. This is the blue graph. So I've designed a transducer array to focus right at 8 centimeters, and I'm getting so much power. So that's option number one. Option number two is to focus slightly inward. Now remember, when you focus a little slightly inward, your focusing efficiency gets better. Your grain of rice gets smaller. So even though you're not at the peak, but the actual power you receive at that focal point is still higher. Right? Does that make sense? Hopefully this makes sense. So I'm focusing now at 7 centimeters instead of 8, but the focus I get at 8 centimeters is still better than the 7. Now the problem with this is that in some applications this is not possible because I have a secondary hotspot. So if you're doing medical imaging and so forth, this is not one of the things you want to do, or any kind of application. You don't want to really go with global max, because global max means that you have a secondary hotspot which you have no interest in, and there may actually be another implant here. But in many of our applications, it's actually, we want to go deeper in this sort of technique. That advantage we have here has to be really utilized. So we can plot at low focus points, these deviations is very small. But as you try to focus in 10, 12 centimeters, the difference is actually pretty substantial. So we start going from focal peak to actual global max as we push the focus inward in the body from a focus strategy point of view. This is showing the ratio, and you see the ratio starts from about 1, but the ratio could actually get to about 2 or 2.5. So you get 2.5 times more power by focusing at an off-peak location. So this just comes from the geometry of the problem. Now, if I plot this versus frequency, think about this versus frequency. Before I was plotting versus size, I can plot versus frequency, and you can see that global max and focal peak are different, but not that different in these distances. Here I'm focusing to, it's a 2 centimeter radius transducer, and it's focusing at 3 centimeters. So this is an F that's smaller than 1, so the focus is pretty powerful. I don't really need to go global max. But one of the things you see is that if my frequency goes down, if I go lower in frequency, I lose my focusing capability. Remember, focusing was a function of your wavelength or frequency. If your frequency is lower, I can't focus as efficiently. And if I go up in frequency, it drops because losses. So there presents itself, given our constraints, given our dimensions, there is sort of an optimal frequency range. And usually for a lot of our applications, these land between 1 and 2.5 megahertz. That's the sort of an optimal range. And it comes from just the capability of focusing, capability of losses in tissue. Now, if you come up with an application that requires to go 1 centimeter deep with a 100 micron transducer, the optimal frequency is going to be very different. Here we're talking about millimeter size and going to 5, 10 centimeters in tissue. That's the optimal frequency range. Of course, when you think about end-to-end efficiency of the system, from transmitter all the way to the receiver, the further out you need to go, the lower that efficiency is going to get. There's no fighting this. It's just from physics. If you want to get a transducer that's operating 10 centimeters deep and it's 1 millimeter, there is a cap of 3-5% of end-to-end efficiency. You can do, this is showing with these particular parameters, you can do slightly better than this by having either 2 transmitter arrays that are focusing together or a larger transducer array. But at some point, you're going to hit a limit. And the limit just comes from propagation of waves, it comes from side lobes, it comes from the energy is not end up at the receiver when you're trying to focus a long way away. Even when you do Fresnel focusing, as we're doing here, we know the transmit comes on the receiver is much lower. We don't have a problem with that. In Fresnel focusing, you might be tempted to think that I can get all side lobes, main lobe peak, energy loss. Okay, so now I'm going to quickly go over some examples of these projects. The first example is the hybrid communication system. So this is the first implementation we did. We said, okay, can you get a power and data downlink on ultrasound? So this is one ultrasound transducer, downlink of power and data. And then we have RF as uplink. And this was our first demonstration. We really wanted to show that we have enough data rate. So we use an RF uplink to satisfy the uplink data rate, which is oftentimes much higher than the downlink data rate. So the system had power recovery and data recovery, and it stored energy for extra functions. So here there's about 100 microamp available at about 1.2 volts to operate any sort of a payload you can imagine. The way the transmitter is probably one of the things that maybe of interest to this community is that we basically had the PPM system, an on-off keying PPM. First, the two pulses, the first one was used as calibration, the second one is really used as data. You can use an MPPM system. There's a lot of different options here on how you want to optimize your transmitter efficiency. So the idea here is that there is an envelope detector that detected the onset of the rise time or fall time of the input data. It generated these 2 nanosecond pulses, and it was turned into a power amplifier to transmit through a coil or a loop antenna, a tiny loop antenna there. A big problem is when you think about total efficiency, you're thinking about energy, not power. So the name of the game is an oscillator that comes on and off as fast as possible. So we made an asymmetric oscillator. This has been used in the community in lots of different places for ultra-wideband. Usually, if you look at literature, people have come up with a way to turn on and off the oscillator much faster. So what you do is you have an asymmetric drive to the oscillator, the VT1, VT2. These two voltages are driven out of sync intentionally so that the oscillator turns on. It's switched into one side, and the turn on is much faster. And so this is showing the output pulses. We have about 9 picojoule of pulse per energy. So that's about 1% of our supply voltage or supply energy goes to each of these pulses. We have a Cascode PA. There's nothing really special about this PA except that it's co-optimized with the antenna so that the antenna and the PA together optimize for power and energy efficiency. Here we have a very small off-state power, about 50 nanowatts, and we're delivering a peak of at 0 dBm into the transmitter. And if you can see here, the peak is pretty high, substantial, and the reason we needed to have a high PA is that the RF link is very inefficient. It's the whole purpose we went to ultrasound. And so the uplink, we really need to push the envelope on how much power we put into the transmitter. We also optimize the transmitter coil for a specific scenario, for alignment, and for about 2-3 centimeters depth. So these are the different impedances and different coil sizes. This is the whole chip with the power breakdown. You can imagine when you have a duty cycle system, this is the beauty of using RF systems. When you have a lot of bandwidth and you can duty cycle down to nanosecond pulses, the energy consumption is very low. This was the whole UWB frenzy of the 10-15 years ago. Everybody was pushing pulse systems for transmitter because there was just no energy being used on the transmitter side. You know when you're sending the pulse, you optimize your hold link, and you're sending picojoule per bit of energy on the transmitter side. Now receiver is a whole different story because you don't know when the pulse is coming in, you need low noise figure and so forth. But on the transmitter side, you can optimize. And this is the same thing we've done here, nothing special. And you can see the whole transmitter energy efficiency, energy part is much, much lower than the receiver and all the other blocks. Most of the energy goes actually to the receiver and recovery. So this is our testing. We did line test about 3 centimeters in tissue. This was sort of a limit. We projected that we can go up to 5 centimeters. We pushed all the boundaries and aligned everything. But when you have an RF uplink, you're going to be fundamentally limited by that link. So next, we tried to do all ultrasound. Forget about RF. It was limited in range. Ultrasound downlink in power, ultrasound uplink. So this was a paper we presented at ICC a few years ago. So the downlink was about 1 megahertz of ultrasound, 50% acoustic to electrical efficiency. So it's pretty good in terms of energy efficiency in power. And we get about 25 kilobit per second on downlink data. And that's okay. I mean, 25 kilobit per second on downlink, most applications, that's that's okay, except a couple like retinal. We have a project on artificial retina, and there 25 kilobit per second is not enough because you're trying to write into your retina, and you need a much higher data rate. But most 90% of applications, this is fine. On the transmitter, we use 2.6 megahertz to avoid the harmonics. We use on-off keying on the transmitter, and we only got 100 kilobit per second. And this is not a surprise because we're using 2.6 megahertz as your transmit frequency, more or less 2.5 megahertz. It's very hard to do, tens of megabit per second on data rate. So that was a limitation that we saw back then. The transmitter uplink data rate is a big fundamental issue here. So these are some of the measurements looking at input harmonics. This is the data at input, and you can also see the output, so that the receiver, we get a lot of leakage from the input, but we avoid them by operating off resonance, off harmonics. This is the data rate. We went up to 10 to the minus 4 bit error rate measurement. We had the PRBS on the chip that could measure up to 10 to the minus 4, and about 8.5 centimeters depth. So this is, and we get about 15.8 dB signal to interference ratio. So these are healthy numbers for uplink and downlink if you're working from a fundamental principle point of view. And these are measurements in tissue that, again, you can see your output spectrum. And these are second generation packages. I'm not going to get into the packages so much, but these are now soft sort of packages compared to first generation. A third example is this reliable. Much about this for the sake of time. But the idea here is that if you have an implant that works at a milliwatt, but also works at 10 microwatts, let's assume you're receiving and you're measuring from parameter, and you also want to stimulate. You want to do that simultaneously. When you stimulate, you're burning a milliwatt. When you're measuring, you're burning 10 microwatts. Now, if you take a sort of a class A operation, quote unquote, if you take an implant that's optimized for a milliwatt, the efficiency is pretty good. Look at the green graph here. The efficiency is decent. Now, you take the same implant and operate it at 10 microwatt, the efficiency is horrible. This is similar to a sort of a class A operation. You're designing power amplifier, right? Because we're not changing the resonant frequency, we're not changing the load, the impedance, all the same. We just have lower usage on the receiver side. So remember I said that the implant or the piezo is inductive from short circuit resonance to open circuit resonance. So I can operate it anywhere in that frequency if I have the right matching network. So what we did in this work is that we tuned the frequency and the matching network. So to maintain flat, sort of a flat efficiency across usage. So I go from milliwatt now to about 50 microwatts, and my efficiency is still above 60% by changing the frequency range and the matching network. So that's one of the things we do adaptively for implants that have a very wide usage, power usage. Third example, that stimulation implant. So we find an implant that can stimulate both, operates 10 centimeters deep in tissue, has data downlink capability, so I can program what I'm writing into the nerves, both in terms of electrical pulse width, amplitude, pulse shape, all of those are programmable. We have a high compliance voltage of 12 volts, and we have programmability, as I said, on the pulse parameters. And we also, in a particular project, because of the application, we wanted to use biocompatible material. So we did not use PZT here. We focused on barium titanate as a use gauge. So this is what the chip looks like. So it has the data power sitting on the left. So there's power recovery and reference generation, clock and data recovery. There's a state machine to figure out what parameters you provide to your stimulation circuits. There's a stimulation circuit followed by an 8 bridge and a switch that goes to four different stimulation sites. Now, normally in our use case, we use 2 of them for electrical stimulation and 2 for LED or light stimulation. But you can use all 4 for electrical stimulation, all 4 for light stimulation. And there is also an off-chip capacitor here for storage. So off-chip capacitor, off-chip electrodes, we're specifically designed for this application. We have to design electrodes that are non-active in the biochemical interface. So use usually platinum electrodes or platinum black electrodes. Then you have LEDs for stimulation, and then you have the piezo. These are the off-chip components sitting outside. So this is what the chip looks like. I used to have a video here of the nerve stimulation. I took that out because in a lot of the circuit talks, I realized this is not such a pleasant thing to show. There's an animal, there's a rat that's showing the sort of a nerve flicking. And after a few versions of this talk and looking at the feedback from audience, I decided to take that out. So imagine this stimulation is now, this is all tested all the way in vivo. And the way it works is that you can provide a controlled, fully controlled charge balance pulse of different amplitude and different width together with the electrical part. And the reason with electrical and optical is that a lot of applications, the neural pathways. So that's why sort of came in. This is again a second generation implant. You can imagine this is a soft implant, so we use polyimide substrates. We use PDMS and Parylene C interfaces for making sure water doesn't get in. And so everything is kind of a soft implant, and you have two platinum electrodes sticking out and the LED sitting on top. So we tested this about 10 centimeter of castor oil, 6 centimeter of porcine tissue, and we can stimulate to about 5 milliamps of current with a barium titanate package, barium titanate piezo. The third application is pressure sensing. So we've shown that we can do stimulation, and I encourage you, if you have any questions, email or look at the papers if you want to go into details of these. But the third one that hasn't been done as much is sensing. So sensing is a little bit more delicate because we're now talking about low signal to noise ratio. We'll talk about high dynamic range. We need precision. It's very different than stimulation. So we started with pressure sensing because pressure is such a vital parameter in the body. So if you look at application of pressure, we have pressure in the eye, intracranial pressure, we have blood, bladder, abdominal pressure. So these are parameters that have diagnostic value. If you can give me the blood pressure coming out right out of the heart continuously for a patient with cardiovascular history, that's a very valuable. And pressure and flow, both. If you give me flow and pressure both, that's of a very high value. For bladder, if you can give me the pressure of the bladder, we can figure out ways to control the bladder. So we wanted to measure with these specs. We wanted to go 10 centimeters deep in tissue, have a resolution of about a millimeter of mercury, and our dynamic range was about 400 to 1200. That's set by bladder. Because imagine a full bladder and an empty bladder, full bladder on earth, on ground, empty bladder on a plane. That dynamic range is about 10 bits. So that's where the dynamic range sort of came in. What's the worst case sort of a range of pressure measurement? And we wanted to do it at a kilohertz. Now, bladder does kilohertz. We don't really need to empty our bladder at the kilohertz frequency. But a lot of parameters when you're measuring blood pressure, we sort of designed a generic sort of implant. Now, this is what the implant generally block diagram looks like. And our first generation had two transmit and receive. So we had a piezo receiving power and data, and a piezo transmitting out data, the pressure data. So we have a pressure sensor with a front end, SAR ADC, finite state machine, and transmitter. And then we have a power management ultrasound detector that controls the whole blocks from the power that comes in from ultrasound. So this is sort of a very high level block diagram of the system. In the second generation, we did a TDD twist. What I mean by that is we use the same piezo for transmit and receive. We just time multiplex from transmit and receive perspective. So from a timing perspective, if you look at this on the bottom left, we start from an ultrasound power coming in. Then we have a quiet period, a wait period. We want all the ultrasound to die down. Remember, ultrasound is a pressure wave, and here we're measuring pressure. So you don't want to have a pressure wave as you're measuring pressure because there's always going to be some harmonic, imagine sort of an IM2 effect that change your DC pressure. So we have a wait period after the ultrasound power to let all the echoes dissipate. Then we start, this is the end of ultrasound, EOU. Then we set up, there's a setup time, there's a sensing time, and then we send out the data. So all of that repeats in every millisecond. So every millisecond we measure pressure recording and we transmit out. Every time we get a command to measure pressure, fully asynchronous, it measures the pressure in a millisecond and transmits it out. So this is how this particular implant works, and it's fully time multiplexed between transmit and receive. One piezo does both. So here are the measurements. This is sort of a pressure measurements that we've done. Again, a second generation packaging, soft packaging. This one is very long. Intentionally, for surgical purposes, going into the bladder, you need to have a very tiny cross section, but it's okay to be longer. So this is about 7 millimeters long, but about 1.5 millimeter wide. So this is designed to be injected into the bladder, no open surgery. And this is pressure measurement going up and down, and this is sort of a INL, so to speak, or of your pressure residual. So our resolution, the point is we get about a kilohertz frequency for about a millimeter of mercury of resolution. And my last project example that I'm going to give, this is a little involved, so I'm going to give you a very high-level overview, and I'll let you look at the paper if you're interested. the question we wanted to answer is, can you make these implants also image internal organs? And there's a lot of applications. I don't want to talk about the applications. There's a lot of speculative applications. There's some more concrete applications. There's all debate. But the idea from a technology point of view was, can you make an implant that's wirelessly powered but also does imaging? Imaging is far more complex in terms of circuits and power consumption compared to sensing. Sensing is 1 kilohertz. It's 1 scalar parameter. Imaging, we're talking about net data rate. If you have to take an ultrasound imager, we're sampling at 20 megahertz, or let's say 10 megahertz, 20 mega sample per second at least, 16 channels. Multiply these out, we're talking about gigabit of data. So imaging is a completely different ballgame compared to pressure sensing. So what would be useful? What would be the use case? So the specs we set out here, I have the block diagram of the system looking in the center. So this is a thermoacoustic imaging system. So it consists of 2 parts. One is stimulation. So you need a laser or an RF source that's pulsed that generates the stimulation. If you're familiar with photoacoustic, thermoacoustic is almost the same. It just uses an RF source. So that's external. External to the body, I have a laser source or an RF source that generates the stimulation. This is RF pulse. Comes in to stimulate the tissue so we can receive the ultrasonic response. Now, on the chip, we have an ultrasonic receiver array that's measuring the response from this pulse, but it's powered and controlled completely by the external device that's a wearable. So the wearable device sends power and data, or receives the data from the implantable imagers that are sitting around tissue, and this CMOT array or ultrasonic CMOT array receives the data, averages it on chip, because we don't have a gigabit per second data link, averages things on chip, and about 1 to 2 frames per second sends the data out. Right? So that's the whole purpose of this. It's designed to be long-term usage, high resolution, full wireless, give you in vivo capability, and it's a multi-modality imaging system. It uses RF or optical together with acoustics. This chip is a little bit more complicated compared to the other chips. So we need to have not only 16 receiver channels, but we need to calibrate these 16 receiver channels, because usually when we have ultrasonic systems, we have a lot of calibration phases with known transmits, with known pulses. Here we don't have any of those. It's integrated with a CMOS transducer that's different from one batch to the next. So what we do is, in every cycle of measurement, which is 1 or 2 frames per second, we inject calibration signals throughout the chain, from input of ultrasound through leakage and surface waves to the receiver prior to LNA, after the LNA, before the ADC, and so forth. So that's how we calibrate all components of the chip. It has about 70 micron of actual resolution, translating to about 30 megahertz of bandwidth. We do 1.2 centimeters imaging window, so the whole window is about 1.2 centimeters. So inside of that, you have about 100 micron resolution. So this is not for, obviously, it's inside the body. It's not for 20, 15 centimeter resolution. So the implant only sees the couple of centimeters around it. The energy usage per frame for image is substantially higher than what we had before, because the complexity of the system is 1.4 millijoule per frame. So we're improving that in the next batch. A lot of that actually went into our memory system. Wasn't designed the way it should have been, probably, and it operates about 10 centimeters in tissue. So these are some of the measurements that are ongoing in the system. We have initialization and synchronization phase. We have AFE calibration, so we calibrate and sense the data, and then we transmit the data on the calibration data. Then we recharge and synchronize when they send the image. So in one frame, you send calibration data, and then you send the imaging data. So you have to send both in a single frame. These are some of the images we are obtaining. So this is electrically excited image. So we actually have an electrical system that generates ultrasonic waves. We have a piece of resistor that generates electrical ultrasonic shock waves, and we receive those. That's shown on the top right and shows you the resolution we're able to achieve at about 1.2 centimeters. We're getting about 100 micron of resolution. And then on the bottom, we're showing multi-static and monostatic. So if you have one imager, this is the lateral resolution you get. The lateral resolution is going to be very limited. If you have multiple receivers, you can actually narrow the lateral resolution. If you've looked at MIMO imaging, if you, for example, heard of MIMO imaging compared to SIMO imaging or CISO imaging, you get better lateral resolution. Okay, so let me finish off by MIMO, ultrasonic MIMO. So in all of these systems, one of the fundamental observations we've had is that the capacity of ultrasonic links are limited. And so whether you look at the ultrasonic system that we had to average the hell out of it to go from a gigabit to about, a few megabit per second, Or you look at the retina application where you really need to read a lot of data from the retina. There's 1,000 channels there, 10,000 channels. The problem is going to be ultrasonic uplink. And if your carrier is always going to be limited to about 10 at most, it's very hard to argue for 100 megabit per second data rate, even if you have high SNR. The modulation index you need for that is going to be large. It's not going to be very efficient. So we started looking at MIMO, just like people have done line-of-sight MIMO in RF links. We started looking at line-of-sight MIMO in ultrasonic links. And the idea of line-of-sight MIMO is that, you have a we're able to invert the matrix and generate multiple receive and transmit channels that are separate and identical and increase the capacity. In ultrasonic MIMO, you do the same thing with the line of sight. And the way you do it is you have Rayleigh spacing between your channels. Once you generate sufficient Rayleigh spacing between these channels, even though this transmitter's data goes to all receivers, if there's sufficient distance between these channels, the phase shift between the receiver channels is going to be sufficient for orthogonalizing the receivers. So this is how line-of-sight MIMO works. You have transmit receivers, there's no scattering, but the spacing between transmit receive is such that you can recover by utilizing the phase information. And I'll show you that in a second. So this goes back to, there's a lot of references here. I really like David Miller's paper because he took a very fundamental approach in figuring out capacity between two volumes. He takes an optical approach and says, if you have volume A and volume B, what is the fundamental capacity between A and B? And he takes an SVD approach and really solves that problem a little bit more fundamentally. So, but there's also Maddow's work with the line-of-sight RF links, and there's going to be Paul Rogers' green MIMO, he calls it green MIMO. All of these were done in RF domain. And so our mission was to show that this also works as physics tells us it works in ultrasonic domain. So just to give you a high-level overview, the way it works is that you have data from transmitter going to the two receivers. There's a 90-degree, imagine simplifying it a little bit, 90-degree phase shift from one receiver compared to the other. So this channel and this channel are 90-degree apart. So now when I receive the data, there's going to be a phase shift between these two data rates. So if I take a sample of the receiver 1 and combine it with a phase-shifted version of receiver 2, I'm able to separate out the blue and the red. Right? So I have what I call here is called the channel separation network. It takes all the receivers, applies the right multiply and add a complex weights, and then sums it and gives you back the original data rate, original data links. So we actually, this was some earlier work we did a couple of years ago. We proved that the concept of ultrasound MIMO works. So we had receiver chains, 5 centimeters, a megabit per second. We did QPSK. And we showed we can double or quadruple the data rate with ultrasonic MIMO link in a water bath. Now what we're doing is, if you look at a real channel, there's a lot of alignment and phase shift dispersion issues that come. But the theoretical fundamental measurement data we had for two different channels after channel separation network. But the fundamental concepts are there and should work. So with that, let me conclude by saying I think what I tried to do today is give you an idea of what ultrasonic power and data could do for a robust implantable platform. I think the real advantage of these systems are going to be for applications where you go deeper and smaller. If you're close to the tissue, to skin, and you have a large implant, I think coil transfer is very efficient. It's FDA approved, it's robust. This is a technology for all applications. So I hope I sort of gave you an overview of various different capabilities as very different examples. Of course, everything was limited to 3 or 4 slides. So I did that compared to going through 1 or 2 projects very deeper. So one of the things I hope you do is you take a look at the papers or you reach back, and if you have any questions, let me know. At the end, I also talked a little bit about ultrasonic MIMO. I think fundamental issue of ultrasonic data communication is a fundamental one for a lot of applications, and I think MIMO can overcome at least a lot of this gap. Not maybe all of it, but a lot of this gap, and so we're looking forward to that. In our group in new directions, we're looking for specific applications. Now we've shown that the basic principles work. We're looking at specific applications, a lot more collaborations. We're moving a lot of these in vivo. We have a collaboration with FDA, which they're doing long-term studies. They've implanted something in now for about 4 or 5 months to see if it's still operational. And an in vivo study means that, speaking, we need to be a lot more robust. So the we took one of these in vivo, we realized there's a lot more questions to be answered here in terms of the packaging really didn't work well. The first time we had an ingestible system, I remember we recovered the implant, but it was all chewed up. We hadn't thought about, well, you put it in the mice, first thing it's going to do, even if you try to push it in, it's going to reflex, it's going to come back, it's going to chew it. So we got to chew them. So that was a lesson to be learned, and you don't want to chew things when they go down, when you have a pill. But so there's a lot of these secondary questions that come about when you go to in vivo studies that have really humbled us in terms of complexity of really an end-to-end system. With that, I'd like to acknowledge the contribution of the students who did all the work here, and also our collaborators and funding agencies. Thank you.